Today's topic is atmospheric stability. So what do we mean by stability? That is the consequence, not meaning. That is again example of stability. Stable area. What do we mean by stability? Energy? Equilibrium. Okay.
It won't change unless an external something from the external is applied.
So energy is in equilibrium. That's better. When the things are in balance. Right. Unstable means there is an imbalance. जैसे एग्जाम्पल दिया था मैंने, मेरे कंधे पे प्रज्ञा खड़ी हुई है. That is a stable condition. Reverse is unstable condition. When instability happens, what is exactly there? What actually happens there? There will be imbalance, there will be movement. Right? In the case of atmospheric stability, it means the general condition of atmosphere, general condition of the atmosphere which resists vertical movement of air. Right? So, the moment we say vertical movement of air, it is directly related with cloud formation, precipitation. Right? So obviously stability, as far as the importance of stability is concerned, that will be very, very important with respect to weather phenomena. And in stable condition, atmospheric instability is exactly opposite of stability, which will promote the vertical movement. Right? Which will promote the vertical movement. So now, this condition, if you look at the vertical movement in air, plays a vital role in all sorts of condensation, saturation, wet air and all. Right? Now, when we say vertical movement, it is basically associated with a parcel of air, a column of air. Right? Any column of air will keep on moving higher up if it is lighter than the surrounding area. Hopefully we understand that. That means the temperature of this parcel of air, temperature of this air column must be lower than the temperature of surrounding atmosphere. Any doubt? Because even when we say density and all, density is primarily responsible for the vertical rise. We can have a very general example of a balloon. Right. Let's say suppose we are talking about a particular part of the atmosphere. The temperature of this air column must be higher than, yes, higher than, density must be lower, higher than the temperature of surrounding air. Thank you, Jana. So let's say suppose this is a balloon, right? If the density of this balloon is less than this area, it will rise. right? If density is equal, then this area, it will remain here. If the density is more, it will sink down. Is that clear? Hydrogen balloon rises from the ground. Why? क्या कर रहे हो यार तुम लोग? आराम से. Its density is, suppose if the surrounding air density is more, the temperature here is more, and the temperature here is less. So it will be denser, it will be lighter, right? So the buoyancy will not be generated. पानी का example ले लेते हैं. It's a very good example is, if you put something which is less denser in water, it will always come out on the top. That's what you call buoyancy. So the buoyancy is dependent on density, and density in the case of atmosphere is dependent on temperature, right? So when we say vertical movement, it is about buoyancy of the air, right? An air column will remain buoyant if it is lighter than the surrounding area or forced by external force to rise. So we are getting that point, right? That external force is available only close to the ground, right? Otherwise, it will not. So whether it has to rise on its own, or it has to be forced to be risen up to a certain extent, and thereafter it will rise on its own, or it will never rise. So there are three situations, three types of stability, right? Now, when we say it is a comparative analysis between a parcel of air, that is density of the parcel of air, and the density of the surrounding air. Right? If the density of this air is more than this, it will keep on rising. If the density of this portion is less than this, it will not rise, it will sink. It is simply heavier and lighter. A lighter particle will always rise. Now, the air parcel also loses temperature. Density is temperature dependent. So, how the temperature of these two relative object will be determined? The temperature in any layer of the atmosphere will decrease as per the normal environmental lapse rate, right, which is a function of many factors. Right? The density of the rising parcel of air or the temperature will decrease as per the adiabatic lapse rate. Is it clear? So it is basically that may be a possible question. Establish a relationship between stability, environmental lapse rate, and adiabatic lapse rate. Getting that point? So if the environmental lapse rate is steeper, it increases the chances of stability or instability. environmental lapse rate is steeper. Instability?
Air can rise fast.
Stability. Instability. Right? And if environmental lapse rate is gentler or less than adiabatic lapse rate? Sorry? So that's how, with respect to the environmental lapse rate and adiabatic lapse rate, there are three types of stability. One is absolute stability. Another one is absolute instability. The third one is conditional instability. Simply determined by the relative condition of environmental lapse rate with the adiabatic lapse rate. For a particular time, environmental lapse rate will be quantified with one constant figure, whereas adiabatic lapse rate varies depending upon the relative humidity of the parcel of air concerned. It is quantified with respect to dry adiabatic lapse rate and wet adiabatic lapse rate. Right? 5 degrees Celsius per kilometer, 5 to 10 degrees Celsius per kilometer. Hope we understand this part. For any given point of time, the environmental lapse rate is roughly uniform. I am not talking about whether the steepness will not be there. Initially, the rate decrease will be much steeper. Thereafter, it will be relatively gentler. Right? So, one single way it will be. But in the case of adiabatic lapse rate, it will be determined by dry adiabatic lapse rate and wet adiabatic lapse rate. Right? If the relative humidity is higher, that means rate of cooling will be lesser. So temperature of air at a greater height will be relatively more if the relative humidity at the ground is more, right? This is the case of absolute stability, right? You can have this diagram when the environmental lapse rate is lesser than both dry adiabatic lapse rate and wet adiabatic lapse rate. Now look at here, environmental lapse rate is lesser than that. So obviously that means 5 degrees Celsius or 4.5 degrees Celsius. You can take any example less than 5 degrees Celsius. So absolute stability is a condition where environmental lapse rate is less than wet adiabatic lapse rate. This will ensure that any particular layer of atmosphere is warmer than the rising parcel of air. That's what you see here. They have given example of 20 degrees Celsius at 1 kilometer, 5 degrees Celsius is decreasing environmental lapse rate. So 15, 10, 5, 0, minus 5. Now a rising parcel of air, when it is dry, the rate of decrease will be 10 degrees Celsius per kilometer. So when on the ground it is 20, at 1 kilometer it is 10 degree, so here it is 15. So surrounding air is warmer as compared to the rising air. Expansion cooling, adiabatic cooling. So initially the dry adiabatic rate, it will cool down. So at, look at here, 2 kilometers temperature is 0 degree, its temperature is 10 degrees Celsius. Here it is minus 6 and it is 5. So every layer of the atmosphere, is warmer than the surrounding air. Right? So that's why the rising of air will be relatively blocked. For some reason, even if it is forced, what kind of cloud formation do you expect? Sorry? Layered clouds, stratified clouds, scattered clouds, because cloud formation will not be very perfect in that condition. Right? Since the air is not buoyant, so in a stable condition, the formation of cloud will be restricted. Hope we understand this situation. You can make this diagram on your page. Basically this one, this part, to understand if the environmental lapse rate is lesser. So temperature at each layer of the atmosphere will be more than the rising air parcel. Hopefully we are understanding this part. Should I try it again? समझ में आ रहा है? Right? So at each layer of the atmospheric temperature will be more than the rising air. So when the air which is rising has reached at 1 kilometer, its temperature is 10 degrees Celsius and the temperature of the surrounding area is 15 degrees Celsius. That means it is cooler. And because of being cooler, it will be heavier. And they will have the tendency to sink down. So only the external forces can lift it up. So that lifting will not be very perfect. That is a stable condition. No, this is for dry air. Now look at here, even here it is for wet air. Saturated air, that's what you call lifting condensation level. So at the point of lifting condensation level, look at where the condensation has started, is roughly around 2 kilometers. So at here, the rising air, 10 degree cooler than environment, that's showing that dry adiabatic lapse rate. So thereafter, look at here, 6 degrees Celsius per kilometer. The decrease of wet air is less. The decrease of dry air is more. So at 1 kilometer, the adiabatic lapse rate is 10 degrees Celsius per kilometer. Second also 10 degrees Celsius per kilometer. At third it is 6 degrees Celsius per kilometer. What do you mean by wet air? Yes. There is no addition of moisture. What do you mean by wet air? When the relative humidity reaches 100%, the air is saturated or wet. So initially when the relative humidity is less than 100%, the air is dry. It is, if it is 100 or plus 100%, it is wet air, saturated air. So in a saturated air, the decrease of temperature will be lesser as compared to a dry air. And even in the dry air, if the relative humidity is very less, the rate of decrease will be very high, right? So that's why even the relative humidity, like when we talk about the factors affecting stability, so these will come into play. Could you make it? This diagram is given in your notes also. Hopefully today it will be ready. So absolute stability is a condition of the atmosphere which does not allow the parcel of air to rise unless they are forced. Since the air is not rising, even the adiabatic lapse rate does not come into play. This situation is produced when the environmental lapse rate is lower than even the saturated or wet adiabatic lapse rate. The most common stable situation is experienced during temperature inversion condition. hope you understand. Temperature inversion condition is the perfect example of a stable atmosphere. Right? Since it restricts the vertical rise of air, the chances of condensation, cloud formation and precipitation are almost nil. During winter season, such situation may cause fog development and affect transport and communication. However, due to forced uplift along the slope of a mountain, frontal wedging etc. may produce some scattered, horizontally spread stratus clouds. Now, what will happen? Even along the mountain, let's say suppose the wind is forced to rise along the slope of the mountain because it is coming from higher area. It will immediately sink here. So if the mountain has sufficient height, there may be a possibility of cloud formation, that is stable condition. Atmosphere is stable. But in a stable condition, what will happen? When a mountain is here and the air is rising along the slope, in a stable condition it will rise further. This is the difference. This is the unstable condition. When the atmosphere is unstable, the air will keep on rising even beyond the slope of the mountain, and they have greater chance to form clouds and produce rain, even somewhat along the leeward side. This is the difference between even the forced uplift along a mountain range in a stable condition and in an unstable condition. Frontal wedging is the best example of a condition where temperature inversion exists, yet you have cloud formation. We do have a brief idea of front, that when the two air masses having differing properties comes and rise, this is the warm air, right? when warm air is forced along the wedge of a cold air mass. So all below you have cold air and you have warm air. So the condition is of temperature inversion, right? Yet you have chances of cloud formation. But the vertical growth of cloud will not be possible in the case when atmosphere is stable. We are getting that. Second is absolute instability. Absolutely unstable. What should be the general condition of the atmosphere? Such that the rising parcel of air is warmer than the surrounding atmosphere or atmospheric layer throughout till tropopause. This is produced when the environmental lapse rate is steepest possible and is more than dry adiabatic lapse rate. Consequently, each layer of the atmosphere remains cooler and denser as compared to the rising air parcel. Making the parcel buoyant throughout its journey. This situation is common during hot summer afternoon when intense heating of ground produces steep decrease of environmental temperature. It is further enhanced when the rising air is from the water bodies. Thus, with higher relative humidity and lesser adiabatic cooling rate. The condition is very favorable for the condensation, cloud formation and precipitation. Most common type of cloud would be towering cumulonimbus, and precipitation will be in association with thunder and lightning. Heavy downpour may very often lead to flooding and increase in river regime. Steep environmental lapse rate.
Steep decrease on like this one, na? Ground will be most heated up. Steep decrease in like this lapse rate.
Lapse rate is steeper, then each layer of environment will have lower temperature, hence denser air. So that's why the warmer air and lighter air will have the chances to rise.
Steep decrease in environmental temperature. Steep decrease in environmental temperature due to intensity of ground. How will be steep decrease?
Because the ground's temperature will be very high and the atmospheric temperature will be relatively lower. So the decrease will be very steep. Environmental is heated primarily from the surface heating, ground heating. So when the ground temperature is very high, and the atmospheric temperature at, let's say, 1 kilometer or 2 kilometer is very less. So decrease is what? Very steep. So environmental lapse rate is very high. Right? This map is not properly visible, yet we can use it. जितना भी दिख रहा है उतने हम यूज कर सकते हैं उसको. Look at here, the steep environmental lapse rate is very steep, right? Even lesser than the wet adiabatic lapse rate. Right. Now what happens? The environmental lapse rate is lesser, is more than even dry adiabatic lapse rate. Sorry. Instability situation is when environmental lapse rate is even more than dry adiabatic lapse rate. That means dry adiabatic lapse rate at the most is 10 degrees Celsius. So you can take example of 10.5, 11, 11.5, whatever. Don't take it fixed from the books. Right? So take it anything more than 10 degrees Celsius. So in particular layer of the atmosphere, if suppose the ground temperature is 40 degrees Celsius. So the air which is rising will also be having 40 degrees Celsius temperature. Right? Now at 1 kilometer, the temperature of the atmosphere would be 11 degrees Celsius less. That means 29 degrees Celsius. At this temperature will be 30 degrees Celsius. Right? So it is warmer as compared to the surrounding area. At 2 kilometer, the temperature would be, in this case it will be 20 degrees Celsius, here it will be 18 degrees Celsius. Hope we are getting that. At the moment saturation takes place, now the adiabatic lapse rate will be as per the wet adiabatic lapse rate, that is 5 degrees Celsius per kilometer. So the temperature at this kilometer will be hardly 14-15. Here the temperature will again be 11 degrees Celsius less, that is 7 degrees Celsius or so. Getting my point? So at each layer of the atmosphere, the temperature of rising air will be more than the temperature of the surrounding air. And that situation creates a perfect instable condition. Hope we are getting that. So the environmental lapse rate is even greater than the dry adiabatic lapse rate. कुछ दिमाग में complexity तो नहीं आ रही है ना? Sure? Huh? Difference in? Because in a very instable condition, the rising air will be very fast, no obstruction, nothing. Just for example, let's take example of a hot air balloon, right? So initially when its density is less than the surrounding area, it will rise, right? If the density difference is very high, the rate of rise will be faster, right? After a point of time, when it is equilibrium level is where the density of the surrounding atmosphere is similar to that of hot air balloon. It will not be able to rise, neither it will be able to come. So what it will have? Horizontal movement. So the air which is stable, which is rising in a stable condition where atmosphere is resisting its rise, the rise will not be perfect vertically, rather it will be horizontal more. So the stratus cloud will be formed in a stable condition. But in the case of when the atmosphere is very perfect or suitable for the rise of air column, so then the cumulonimbus cloud will be vertical growth of cloud. Once they start forming, they will start forming. There is no inhibition, there is no stoppage, there is no restriction. So cloud growth will be vertically dominated. It's not that a stratus cloud will not be there in that condition, but they will be dominated by cumulus variety. The third is conditional instability. conditional instability. That means instability is subject to certain condition. This is a situation where atmosphere is stable initially, then unstable after lifting condensation level. That means environmental lapse rate is in between wet adiabatic lapse rate and dry adiabatic lapse rate. So, till the lifting condensation level, the atmosphere is stable, but thereafter it is unstable. In such condition, external force must be there for the air to rise till the lifting condensation level. And then release of latent heat and the difference in the wet adiabatic lapse rate and normal environmental lapse rate will make the air automatically buoyant. This is the most common condition of instability found in the real world. Undulation along the ground convergence, frontal wedging, coastal slope, etc. are the external forces which have to lift the air till condensation level. Such situation is conducive for all varieties of clouds and may lead to moderate to heavy rainfall in a region depending upon the moisture condition of the air and the intensity of external force. Such situation is conducive for all varieties of clouds and may lead to moderate to heavy rainfall in a region depending upon the moisture condition of the air and the intensity of external force. Like the ocean, like this one, coastal areas. The slope will also be acting as a wedge.
Not that much steeper casual slope, right?
Even in that case, the air will start piling up. So that because of piling up, the air may have vertical rise. So may be forced to rise up till there. Like for example, just see suppose in the coastal areas, the air is smoothly coming, right? Let's say from monsoon, case of monsoon also. So the moment this is supposed to rise along the slope, that's one of the ways to lift the air. So when it is rising along the slope, the speed of the air will be definitely lesser as compared to the speed which is coming. So simple mathematic principle, there will be piling up of air. The air will be accumulate here and they will rise. Frontal wedging, I hope you can easily understand. Besides, the stability and instability may be associated with the movement of an air mass away from its source region. For example, if a cold air mass is moving over a warmer water surface, it will be warmed and moisture will be added from below, leading to instability. A common example is the Great Lakes of USA during winter season. water bodies of Arctic Ocean and Siberia. If the warm air mass is moving over the colder surface, this will produce stable condition. ठीक है? There are three possible questions here from this topic. Direct question: what do you mean by atmospheric stability and instability? Explain various conditions producing stability and instability. Write down the question. What do you mean by stability of atmosphere? Explain the conditions responsible for stability and instability. Second question: establish a relationship between stability, environmental lapse rate, and adiabatic lapse rate. Next question: discuss the factors responsible for variation in the condition of atmosphere leading to stability and instability. I hope first two questions will not have any problem. Third question: factors. What are the factors you may have? Sorry? Factors affecting stability and instability. Differential heating of factors affecting stability. All we have talked about. Just think over it. Stability and instability. What is the most important factor? Density of what? Of air, parcel of air which is rising, right? That will be determined by temperature, and that will be determined by, sorry? Environmental lapse rate. Sorry? Terrestrial radiation. So environmental lapse rate, that's the crux. Terrestrial radiation ultimately will determine environmental lapse rate. So if the everything we have talked about on the line of environmental lapse rate only. If the environmental lapse rate is very steep, instable. If it is very gentle, stable. If it is in the middle, conditional instability. Right? So, primary reason is the factors affecting the nature of environmental lapse rate. Right? You can explain it. Suppose if the question is directly, explain the factors responsible for generating stability and instability. Then talk about factors, give example the same, conditional instability, absolute stability, absolute instability. यहाँ पे बात करेंगे उसी context में. Then the second is the relative humidity of air. Close to the ground. How it is so? Because it will affect, yes, adiabatic lapse rate, plus it will determine height of condensation. Right? It will determine the height of condensation, that is dew point temperature. Hope we are reaching there. नहीं समझ रहे हैं हम लोग? The third factor, now nothing but these two, the factors affecting these two. Yes, surface condition or nature of the surface over which the air parcel is rising. यहाँ पे हम कह सकते हैं ओशनिक वर्सेस कॉन्टिनेंटल. Then topographic barrier creating friction, piling up of air, acting as external force. Factors affecting temperature inversion. Hope we are understanding it. So if you explain this in different perspective, you will get the factors affecting stability and instability also. कंटिन्यूटी में रखना है इसको. तो यहाँ पे एग्जाम्पल दे सकते हैं फैक्टर अफेक्टिंग टेम्परेचर इन्वर्जन के बाद the conditions, the pressure condition on the ground, pressure conditions on the ground, high pressure, that is pressure condition on the ground, high pressure, subsiding air, stable condition. Low pressure, rising air, in a stable condition. So all the areas of low pressure are areas of instability, and all the areas of high pressures are areas of stability. Intense heating or cooling of a localized area. Right? If it is water bodies and heating, it will produce in a stable condition. If it is land areas and cooling, stable conditions. Right? Generally associated with tropical cyclone, thunderstorms, dust devils, tornadoes, etc. Sorry. Any question? नहीं है, सब समझ में आ गया.
ये जो आर्टिफिशियल रेनफॉल होती है, तो इसमें सिल्वर हाइड्रेट होते हैं. तो ये हाइड्रोस्कोपी जो निकले हैं, ये इसमें ऐड करते हैं, तो ये सिल्वर हाइड्रेट.
अब तो आसान हो जाना चाहिए चीज़ों में तुम लोगों के लिए. सिल्वर आयोडाइड क्या करता है? इंजीनियर्स क्वेश्चन बढ़ाता है. It acts as a hygroscopic nuclei as well as it decreases the temperature of the area. बस वो सिंपल सा प्रिंसिपल है. Whether it is you want to go for artificial rain, you don't want to go for it. If you don't want to allow the clouds to precipitate, तो क्या करेंगे हम? Hygroscopic डाल दो या टेम्परेचर बढ़ा दो. The very infamous one during Olympics of China, Beijing वाला Olympics में, China has left lot of missiles into the clouds to increase the temperature so that rainfall doesn't occur. And several unbelievable consequences are expected from the scientists that what is happening in South China Sea is associated with that. So artificial rain, if you want to go, so whatever moisture is there in this area of the atmosphere, you go and freeze them, you will have rainfall. Decrease the temperature of the air, if up to the extent that you can form clouds and then let it fall that way. So chain reaction is also needed. Berggren process, collision-coalescence process. So it's cloud formation, then you develop the chain reaction. For that you just extract a good number of hygroscopic nuclei. That way. Putting silver iodide, if it is simply hygroscopic nuclei, it will reduce the chances of rainfall. Remember.
We have to increase the temperature. We have to fulfill two conditions, right? Add some moisture or increase the temperature.
Decrease the temperature to increase relative humidity. Atmospheric circulation. Atmosphere circulates, that is dynamic. The atmospheric circulation. The atmosphere is not static. Rather, it keeps on moving. That's what we call atmospheric circulation. Right? Atmospheric circulation. Circulation is nothing but movement of air. Right? Movement of air is always associated with PGF TGF is basically a function of temperature gradient, right? Temperature gradient is basically a function of a differential insolational effect, right? That's what we call north-south energy imbalance. This may be correlated with atmospheric circulation as a question also. Right? North-south energy imbalance. If you look at the overall insolation temperature pattern, roughly around 90 degree, 40 degree, 0 degree, 40 degree, 90 degree. The latitudinal position. If you look at the insolational aspect, we'll start from here. If you look at the terrestrial radiation, this is insolation, this is terrestrial radiation. Look at here, overall deficit energy or energy deficit area, energy surplus area. This diagram should be used in temperature discussion also. This is what we call north-south energy imbalance. Roughly around 40 degree north to 40 degree south is the energy surplus area. And 40 to 90 degree is the energy deficit area. That produces north-south energy imbalance, resulting into the pressure gradient force and then the atmospheric circulation. Various ways to discuss it and the questions may be asked. First is meridional circulation. And the second is zonal circulation. Meridional along the meridians, that is longitudes, that is north-south component. Zonal circulation, basically latitudinal circulation along the latitude, that is basically primarily west-east component. Zonal. When we say zonal, it is latitude. This is poles to pole is longitude. So north-south component or south-north component. When I am saying north-south does not necessarily mean unidirectional. It may be north-south, south-north both. West-east, east-west both. Right? So here if you see this part, the most important example is westerlies, the example of jet streams, the example of Walker circulation. The jet streams will be both polar front jet stream, tropical westerly jet stream. The Walker circulation is basically equatorial or tropical zonal circulation. Meridional circulation is basically tropical cell or Hadley cell within the tropics. That includes trade winds, surface, anti-trade, upper air. A bit of polar easterlies. Equatorial or tropical zonal circulation. Zonal circulation in the tropical region. That is this way. This is the modern explanation of the atmospheric circulation, where it is believed that it's not necessary that the energy transfer should take place north-south direction. It may take place east-west direction also. Zonal circulation is? No. Equatorial is equatorial and zonal is along the latitudinal area. Equator is a region. So in the equatorial region you have meridional circulation also. When the trade wind is moving roughly along the meridian or longitudes, it is meridional circulation in the tropical region. So the trade wind or Hadley cell is tropical meridional. Walker cell is tropical zonal. ज़्यादा तो नहीं हो रहा है ना?
सर ये वो है क्या जो प्रेशर सेल्स की हम बात करें?
नहीं नहीं, ट्रेड विंड वाला वही है, ये ट्रेड विंड वाला है, वो नहीं है.
Sir, it is classified according to its direction only, right? If it is along the longitude or along the latitude.
सिंपल सा है ना, नॉर्थ साउथ कंपोनेंट भी लिख दिए ना कि इफ रफली इट इज नॉर्थ साउथ इट इज मेरिडियन और closely moving along the longitudes it is meridional circulation, closely moving roughly around the latitude zonal circulation. When we say tropical Hadley cell, what is the Hadley cell? Right, trade wind is also coming from southeast, right, but closely following meridian longitude rather than latitude. So this is tropical meridional cell. When we say Walker cell, that is tropical zonal cell. Polar easterlies is also meridional roughly. मैं भी सोच रहा हूँ कैसे हो गया, निकाल दे क्या इसको इसमें से. नहीं, वेस्टर्लीज जो है ना, वेस्टर्लीज इज, don't compare it with westerlies, because westerlies is the area where the maximum exchange of energy takes place. The frontal formation, a lot of traveling cyclones, and most of the disturbed weather phenomena, not the devastating. The weather is highly dynamic in that area of the middle latitude region, because that around 40-degree latitude, because that's the actual area where you have the maximum contrast. If you are living in perfectly colder area throughout, doesn't make much difference. Warmer area throughout doesn't make much difference. But that makes difference wherever the contrast is highest. So the westerlies is something different, polar easterly is something different. Even that is somewhat meridional rather than latitudinal or zonal. Easterlies. Easterlies is meridional. Westerlies is zonal. Westerlies primarily associated with jet streams. Forget about which is zonal, which is meridional. I hope you understand what is zonal and what is meridional, right? बाकी हम लोग देख लेंगे आने वाले टाइम में. Then the second way to ask questions and to look into it is also the surface circulation, the upper air circulation. The surface circulation, you start with IPCZ, trade wind, subtropical high pressure belt, westerlies, subpolar low pressure belt, polar easterlies. You explain polar high pressure belt. Upper air circulation, entry trade, subtropical westerly jet, polar front jet. Then next would be modification of atmospheric circulation. Seasonal modification, especially explain the locational pattern. Hemispherical variation, explain the pressure belts of northern hemisphere, especially the semi-permanent cells. The most important modification, monsoon. First the shifting of the pressure belts, and that's what locational pattern, where actually they are located, number one. Then change in the intensity and magnitude of like jet streams. The change in the locational position of jet streams and its impact on weather phenomena. Right? All these will be associated with that. Then the most important one is the scale of atmospheric circulation. Whenever a general question is asked, you start with this. A scale is macro scale, meso scale, and micro scale. Though all of them are primarily interwoven and embedded. Macro scale, basically all the primary circulation. Together with relatively long-lasting atmospheric phenomena embedded in the global air circulation. For example, traveling cyclones, trade wind, westerlies, all will come into this category. Even jet stream. Mesoscale, which lasts only for few minutes to at most few hours. Here we will have tornadoes, thunderstorms, tropical cyclone, etc. Local winds, land breeze, sea breeze, mountain breeze, valley breeze, etc. Lasting from few seconds to at the most few minutes. Best example is dust devil, gusts, etc. What are gusts? Very high speedy wind for a very small period of time. A storm is much bigger. लू नहीं जो हाँ वर्लपूल टाइप का जो डिफरेंट बनता है उसमें थोड़ा सा पार्ट होता है जो डस्ट डेवल गस्ट होता है. माइक्रो नहीं है तो मेसो में भी आ जा रहा है टॉर्नाडोज एंड ऑल. हाँ छोटी चीज ज्यादा खतरनाक होती है पता भी नहीं चलता है. Right? So good part we already have talked about the atmospheric circulation. As far as the surface is concerned, a bit of anti-trade is required. Right? Anti-trade wind is nothing but the cellular motion of that. Right? Now, another way of asking question may be the cellular formation. So we have 3 identified cells, right? 3 ways to cellular motion. First is Hadley, unicellular on a non-rotating earth. Tricellular, Farrell, right, on a rotating earth with the inclusion of Coriolis effect, right? Then we have Parman's model. Again he talks about zonal circulation. That is heat, not necessarily this is the recent model. In this tricellular model we have Hadley cell, that is the tropical cell. Then we have, it is called Ferrel cell, that is the mid latitude cell. And the third one is polar cell, that is the high latitude cell. Mid-latitude circulation can itself be a separate question as well, because that is the most widely studied. Modern explanation is the disappearance of troposphere also. The troposphere very often get disappeared and the entire circulation goes into the stratosphere as well, especially during summer season. Right? Now, starting with why. Why atmospheric circulation? Why there is understanding and there is a need on the causes behind the atmospheric circulation. So atmospheric circulation, the reason behind atmospheric circulation is energy imbalance. So the circulation tries to balance it. Right? In the process, if you look at their contributory factors only, supplementary factor of the heat transfer is ocean circulation. And the ratio is 80-20. 80% of the heat imbalance is balanced by atmospheric circulation and hardly 20% is balanced by oceanic circulation. So obviously heat energy imbalance is basically trying to be balanced. What is the role then? Overall agar human parlance mein dekha jaye. So let's say assume that atmospheric circulation is not there. So the tropics will be hotter and hotter and hotter getting, and the temperate region will be colder and being colder and colder. So Earth might be a place without habitation. That's the importance of atmospheric circulation. So obviously importance lies in the fact that without atmospheric circulation, Earth might not be habitable. Tries to balance the imbalance created by insolation. The reason and the importance also is the same. When we say the meridional circulation, primarily associated with north-south energy imbalance. Zonal is primarily to Coriolis force. Don't go after the words, correct it. The primary problem is mid-latitude circulation is far more complex than the idealized presentation of the real world. This is the area which experience maximum energy transfer, hence is more vulnerable for the weather changes and change in the pattern of atmospheric circulation. On the ground, the condition is somewhat disturbed because of topographic and other barriers, whereas the upper air flow is more zonal in nature. The ground barrier produces many breakage in the normal flow, taking the shape of eddies, whirlpool, like in the rivers. These flow suddenly attains wavy characteristics and have north-south component in it. This meandering component produces several weather phenomena on the ground. Since in the convergence of polar front, the energy exchange is maximum, the frontal zone is the main area of such disturbances. Along the core of these waves, lies the highest velocity wind in the upper air, called jet streams. These streams are very swift, narrow band of geostrophic wind embedded in the upper air westerlies. They are 100 to 500 kilometers wide, few kilometers thick, and thousands of kilometers in length. The speed varies from 50 kilometers to 300 kilometers, and at times reaching even 400 kilometers per hour. Winter season produces highest speed and greater disturbances in this belt. Polar front jet stream lies at 9 to 10 kilometers above the ground over the frontal zones formed by warm westerlies and cold polar easterlies. Initially, it flows from west to east, but once the air mass starts intruding into each other's territory, the jet streams take a meandering shape and may move in north-south direction. Its location basically demarcates the zone of warm wind and cold wind. Origin is primarily associated with thermally induced pressure variation, but the direction is determined by frictionless Coriolis force. In any air column, the pressure decrease is more gentler with warm air and steeper with cold air. Thus, the pressure gradient force becomes very steep and redirected exactly in opposite direction of the ground condition near the tropopause. This steep pressure gradient produces very high velocity wind, especially along the core zone of the Rossby wave. Meandering of jet stream is not only along its path but also with respect to height and place an important role in the formation and track and movement of wave cycles. Akshay, you use shorthand or you have normal speed? That's good, very good. So finally we have understood jet stream. Huh? First let's have some glimpse of visual glimpse of some of the normal circulation. That's the most idealized pattern of the atmospheric circulation you can have. The trade wind zone, the westerlies and the polar easterlies, and the three cells. Basically Hadley cell, that's what you call tropical cell also. Then we have Ferrel cell, then polar cell. Right. This is the most idealized way of looking at the real world. But exactly the situation is very different, especially in the mid latitude, where we are talking about the subpolar low pressure belt and the frontal formation here in between the Ferrel cell and polar cell. Right. And that creates lot of atmospheric phenomena which is relatively very complex.
When polar cell is radially outwards or same direction?
In the polar cell,
Polar cell. Radially outwards. Polar area.
from the polar air. So imagine this globe. Right? This is a polar high pressure area on the ground. So there will be descending air, subsiding air current here, and then the divergence in all directions. So it is, since it is a two-dimensional figure, so you have to imagine in three-dimensional figure. So the polar high pressure area on the ground, so divergence in all the sides. Right? So this is polar high pressure. Then similarly you can expect ideal subpolar low pressure belt, ideal subtropical high pressure belt, ideal equatorial low pressure belt, right? So here you have this situation. If you look at this part, this is the trade wind on the ground, which is visible here, and this is the rising column of air in the equatorial belt, and this is the anti-trade, right? Then descending, this is the location of subtropical westerly jet stream, right? Then you have the westerlies belt. Then the frontal zone, right, and the frontal zone, and then the formation of jet streams here. The westerlies, this cell is the most distorted one. This cell is definitely not in the way of the cellular formation that is being suggested. They create wavy structure, and that's where they take zonal direction. And the zonal flow is a more common fact in the mid-latitude belt than acellular motion. And the heat energy transfer takes place through zonal formation, which ultimately takes a wavy characteristics, direction, and meanders. And through that meandering, it touches the entire part. And thus meandering was first identified by G.C. Rossby, and that's why it is called Rossby wave. Right? has come to this situation. This is the best example of the most widely studied of the North American air mass. Right. Here you will understand the polar vortex also. This is the initial convergence zone. So here this is the axis of jet stream. So initially it is west to east, perfectly west to east, purely zonal. Now the moment warm air will start intruding into the cold air, and cold air mass starts intruding into the warm area. So this takes the wavy characteristics. Right. The wave further gets more angular and they are more meandering. And after a point of time, this low pressure area and this low pressure area, this is called polar vortex, will be left out. And then again, the jet stream will attain the similar axis. Look at here. And this will be disconnected. It will be detached. These two points will be detached. These two cells will be detached and they will start moving independently for a good number of days before they disappear. Sorry? Just like the rear wind. Just imagine the very high speedy wind, speed river for a long distance. So everywhere you don't have meandering. Only the pockets which are more suitable have whirlpool, meandering and all. So meandering of river is somewhat different, but making whirlpool and all is the typical example of jet stream, jet axis. Even jet stream is not throughout the globe. It is found in the pockets of that. Right? As a layman, we can start with jet stream means very high velocity wind. Very high velocity wind will always be associated with very steep pressure gradient. Very steep pressure gradient means very steep temperature gradient. So wherever in the upper air you have the scope of very steep temperature gradient, you can easily understand the formation of jet streams or origin of jet streams. Right? For that, if we try to go through the fronts and then we try to mix it up, you can easily understand it. Right? This is how the polar vortex will move from polar area towards the interior along this line, and that's how the waves will be generated, upper air. When the jet stream axis is deviated and it starts meandering at a much sharper angle, then the polar vortex will move towards the interior and will affect the surface climate as well. This wave may be around 4,000, 5,000 kilometers. One single wave may cover that much area. So that 3 to 4 or 5, 6 waves may cover the entire globe. Within the Rossby waves, you have some smaller waves also. And that smaller waves are associated with weather disturbances. अभी बताते हैं. बना रहे थे हो गया. You can detach in the fifth figure also. Fifth figure में you can detach those cells and show it independently as well. No, this is the ultimate stage. No, every winter there will be like that. But sometimes the severity will be far higher, basically because the problem that we don't have proper knowledge about what is happening in the polar areas, especially in the winter season. Right? So intensity varies depending upon the various atmospheric global conditions. But polar vortex phenomena will be normal phenomena. It is a normal phenomenon. But when it will be very, very severe is an exceptional phenomenon. Just like monsoon rainfall. Right? So polar vortex impeding into an area and far deeper area with greater intensity with more amount of snowfall and all. So that's the extreme case of polar vortex. Otherwise it is a normal phenomenon. Detachment is a normal phenomena, cold waves will be a normal phenomena, but high intensity cold waves will be an exceptional phenomena. Sorry? That's when the jet streams attains greater height and starts having greater meandering, it may destroy the tropopause also. It may enter into stratosphere.
Conditions are different there. If it goes further, the temperature too get increased.
No. This will affect the that's why this is the least studied phenomenon. अभी इसको पूरा इसके consequence, the cause and has not already been discussed. Only the meandering and this mid latitude phenomena may destroy, even the polar vortex may destroy the tropopause, and it may go higher up in the stratosphere, colder areas, but least studied till now. Now, a brief of front, we'll discuss front tomorrow mainly, but brief of front, if you see, the basics of front is that fronts are, like, what do you mean by front? Discuss various types of fronts, discuss whether associated with this. So if you look at the fronts, the term is derived from war front. Right, war front, where a zone is demarcated, and here you have Army X, and thereafter you have Army Y, and this zone, which is kept for the actual fighting, is called war front. Right? In the case of air masses, Army X is air mass X or 1, Army Y is air mass 2. Now these two will converge, but if they vary a lot, that means especially in their physical properties with respect to primarily temperature and moisture, differ a lot, consequently they will not mix up freely. Rather, will make a transition zone of sloping boundary called front. Here you have attacking zones where the wind attacks each other. So how the Rossby wave will form, we are just using that part. Fronts we will discuss tomorrow. Now along this transition belt, let's say suppose this will never be a line, this will always be a zone. So you have the incoming of polar easterlies. Right? And then we have subtropical westerlies. Now this convergence zone is subpolar low pressure. So ideal convergence, we have imagined that this will converge, air will rise there and will make a low pressure area, and this is how cells will be formed. But in practical sense that doesn't happen. Now here when we were talking about the vertical column of air, the difference in the pressure between the two vertical column of air is equally important. let's say, suppose the rate of decrease, that's what we have written also in our write-ups, that rate of decrease of pressure in a warm air column will be less as compared to in a cold air column. Like, let's look at this. If the warm air column is here, and immediately we have cold air column. So since it is cold air, it is warm air, the surface pressure gradient will be obviously like this, right? Here the air parcel is rising. Since it is a warm air, the surface pressure gradient will be like this. But if you look at higher up, since the rate of decrease of pressure is lesser here, the rate of decrease of pressure will be much steeper here. So initially for the close to the ground surface, the pressure gradient will be in this direction. But if you look at this area, they'll start thinning up, higher up. So higher up the pressure gradient will be in this direction. And that may be much steeper than the ground. Right? That causes air to move in this direction. सर्कुलेशन भी हो सकता है, लेकिन यहाँ पे हम दो कॉलम की बात कर रहे थे, इमीडिएट सर्कुलेशन नहीं होगा. जैसे लैंड ब्रीज सी ब्रीज में अगर हम बात करें तो लैंड ब्रीज सी ब्रीज में भी वही होता है, सेलुलर मोशन होता है. यहाँ पे हम सेलुलर मोशन की बात नहीं कर रहे हैं. वी आर टॉकिंग अबाउट द टू कन्वर्जिंग एयर masses. One is warm, and imagine the column of air, right? One is cold when they are converging. So in the convergence zone, the upper air will have a different variation and lower air will have a different variation or different direction of pressure gradient force. Is that clear or not? Right? Now you see what will happen. That's what you call Bay-Ballett's law. As per Bay-Ballett's law, if you are standing in the northern hemisphere taking wind on your back, the pressure on the right side will be higher as compared to left side. This is what Bay-Ballett's law say. Because of Coriolis force turning rightward. So everything is pushed in the right direction. Let's say suppose this dais, if you take. A very good example we can have, we are standing in the northern hemisphere. And the wind is coming from this direction. So all the wind which is hitting the dais will turn rightward. So all the air will ultimately will move from this direction. None will go in this direction, whatever has hit this, because they will be hitting in this direction. So ultimately overall pressure, if you see, because air ultimately will be piling up here as compared to this portion. So any column of air or any horizontally moving air band will have higher pressure in the right direction as compared to its left one. Right? So what I am saying is that this structure, this convergence will have a different impact on different layer. जैसे अगर हम normal army की बात करें, army attack करती है आपस में एक दूसरे के साथ. So wherever the king is standing, he will be much more strongly fortified with all the superhumans around him. Right? So imagine the forces working and moving against each other, and they are trying to fight and kill. So the stronger areas or stronger forces will move far deeper into the enemy zone. Right? And if that army is stronger areas will move, generally king don't come in front directly, face to face. unlike it is shown in the movies. They are generally away from each other. So in this king is this side, this area, king is this side. So they'll keep on intruding into each other's territory. That's a much deeper way, right? In the case of wind, the strength will be determined by pressure, right? So in this band of wind, here, here we'll have high pressure, here we'll have low pressure. Whereas in this band of wind, here you'll have high pressure and here you'll have low pressure. Right? So the attack of wind will be from this side, back beating, back stabbing, and here from this side. नहीं समझ में आया? Sure. Now a straight line which was earlier a straight, that is dividing the pure warm air and pure cold air, which is dividing the pure warm and pure cold air, will now start changing its location. So earlier it was a straight line, now it will be a, look at here, if I try to draw a line, this will be the line which separates the warm air and cold air, right? Next line will be like this, third line will be like this, fourth line will be like this after a point of time. This is what we call Rossby wave. So initially the jet stream which was almost west to east now will start meandering like this. Right? And let's take that wave, Rossby wave. Initial convergence was this one. Now the Rossby wave has taken much deeper this thing. So that means this entire area is occupied by warm air and this entire area is occupied by cold air. That means warm air has moved far closer to the polar areas and cold air has moved far closer to the subtropical areas. And this is warm air. This is cold air. Subtropical areas, equator ward, that will move towards the pole and this will move towards the equator grudge. Sorry? Both have passed the subpolar low pressure. Energy exchange will take place. This warm air will start cooling. Yet the temperature of warm air here will be far, far higher as compared to temperature of cold air here. Without any doubt. Even this cold air will be warmed up gradually during the exchange of energy. ये थोड़ा गर्म होती जाएगी, but at the point when it reaches here, it will be far, far colder as compared to the warm air which is present in the subtropical areas. This is what we call core of Rossby wave. Warm air will intrude into the polar areas. It will be further discussed tomorrow. जब हम फ्रंट पढ़ते हैं टेम्परेट साइक्लोन में भी इसका यूज. Poleward side of the core will be having colder air. Equatorward side of the core will be having warmer air. Right? Poleward side of the core will be having colder air and equator side will be having warmer air. Now the temperature contrast will be very huge. So the pressure gradient force will be very steep and it will produce jet stream in the core of that Rossby wave. And that's how the Rossby wave will form. So actually what we were expecting a cellular motion has now become a zonal motion. Right? The air which was supposed to be there now has moved here. The waves which are supposed to be here now has moved here. And along this line, the entire wave and cyclonic circulation will take place. Second thing what we have written is that the meandering of jet stream is not only with respect to its path, but also with respect to its height. Right? So it's not only meandering this way, but also meandering with respect to height. जैसे ऐसे ऐसे ही नहीं मूव कर रहा है, बल्कि यहाँ पे ऐसे ऐसे ही मूव कर रहा है, meander हो रहा है, ऊपर नीचे भी हो रहा है. मजेदार चीज है. हाँ, very much the ground condition will affect the upper air, but that meandering is occasionally, not everywhere. Right? And wherever this is meandering, if it is rising, it is creating a divergence. This portion is creating a divergence. That means if the air is rising here, they will take it and take it away. And the moment air is moving here, they will create subsidence. So this will create high pressure, this will help low pressure, and that's how local level cyclones are formed, and smaller Rossby waves are created within the larger, more greater, longest wavelength Rossby waves. Polar front, subtropical westerly. कुछ क्लियर है? श्योर? नहीं? हाँ? पूरा तो आज तक मेरा नहीं हो पाया, तुम्हारा पूरा आज तक साइंटिस्ट का नहीं हो पाया, तुम्हारा कहां से हो पाया? The jet stream is again the least understood phenomena, especially among the major atmospheric component, which is so vital for ground conditions, yet it is very less understood. जितना साइंटिस्ट समझता है उतना हम लोग समझ गए हैं, उससे ज्यादा समझने की जरूरत भी नहीं है. न एनर्जी है, न रिसर्च है, न कुछ है, न रिक्वायरमेंट है. So jet streams are basically very high velocity, swift, narrow band of meandering geostrophic fragment. ठीक है? जब हम whenever we talk about the polar front jet stream, it is produced in the frontal zone in the core of the Rossby wave, where temperature contrast is maximum. That temperature contrast in the upper air produces a very steep pressure gradient force, causing the warm air to turn rightward under the influence of Coriolis force in the northern hemisphere. So they have a west to east zonal circulation. So initially they move in the west to east direction, and thereafter they start meandering in north-south direction after the undulation of that Rossby wave, after the formation of that Rossby wave. And gradually it is nothing but the exchange of temperature. You keep on putting cold water over a hot tawa, छन छन की आवाज आती रहेगी, तब तक आती रहेगी जब तक तवा का टेम्परेचर पानी के टेम्परेचर के बराबर नहीं हो जाए, उसके बाद नहीं आएगी. ठीक है? The same thing happens in that middle latitude zones. The air keeps on attacking each other, the exchange of energy takes place, the chan chan ki awaz is in the form of weather disturbances, right? And weather disturbances we call it temperate cyclones, and the higher up in the upper air the same is producing jet streams, and once the area starts equilibrium, then again re-emergence of same front, then wave, then formation, then disappearance and all. Right? किसके? Rossby waves की. Depend करेगा ना. Rossby waves are relatively permanent in nature. Only they keep on changing its location. They'll keep on shifting towards the pole during winter season, keep on coming towards the equator during summer season, winter season. Winter season, they'll keep on moving towards the equator. And summer season they'll keep on shifting towards the, like sometimes the polar front jet stream is merged with the subtropical westerly jet streams. Subtropical jet stream is generally a winter time phenomena. Summer में almost disappear हो जाता है. But polar front jet stream is a permanent phenomena, only with their spatial changes. During winter season, the temperature contrast will be maximum. Hence, the speed is higher. During summer season, the temperature contrast between the converging air mass will be relatively minimum. Hence, the minimum speed, minimum pressure gradient force and minimum speed. ठीक है? टेम्परेचर कंट्रास्ट विंटर्स में मैक्सिमम क्यों होगा? आई होप यू गाइस आर क्लियर अबाउट इट. नहीं नहीं, कोर पॉइंट को आप छोड़ दीजिए. कभी कभी लेमैन की तरह सोचना चाहिए, हमेशा आईएएस ऑफिसर की तरह थोड़ी सोचना चाहिए. इनफैक्ट हमेशा लेमैन की तरह सोचना चाहिए, कॉमन मैन की तरह, विथ इंटेलिजेंट माइंड. मैक्सिमम इन विंटर. मुझे भी लग रहा है इट शुड बी इन समर. चेंज कर दें क्या? चलिए, लेट्स एज्यूम द समर टेम्परेचर ऑफ सब ट्रॉपिकल हाई प्रेशर रीजन वुड बी व्हाट? एवरेज व्हाट? लेट्स टेक अ फिगर 25. थोड़ा कम हो गया. 35. व्हाट डू यू एक्सपेक्ट समर टेम्परेचर ऑफ पोलर रीजन? 10. What is the difference? 25. Winter temperature of subtropical high pressure area? 15. And winter temperature of polar high pressure area? -30, -40 degree. So temperature contrast is कहाँ पे? तो कभी कभी कॉमन से अप्लाई कर लिया करो. एंड सीरियसली इट्स नॉट ये बात, लेकिन कई बार हम क्या होता है कि हम इमेजिनेशन में ले लेते हैं कि विंटर का मतलब है टेम्परेचर, विंटर में तो सब ठंडा ठंडा होता है. हम इंडिया में जहां रहते हैं वही इमेजिन करते हैं. आप पूरा फिर उस सिचुएशन में अपने आप को डाल के टेक एन इमेजिनेटिव फिगर विच इज रीजनेबली क्लोज टू द रियल फिगर एंड देन ट्राई टू फाइंड आउट. नहीं, अब मुझे भी लगने लगा कि टेम्परेचर कंट्रास्ट विंटर में ज्यादा होना चाहिए, बिकॉज आई हैव गिवन यू फिगर्स. तो उसमें जब कंट्रास्ट मैक्सिमम होगा तो टेम्परेचर ग्रेडियंट क्या हो जाएगा? स्टीपर हो जाएगा. जब स्टीपर हो जाएगा तो प्रेशर ग्रेडियंट स्टीपर हो जाएगा, देन द वेलोसिटी ऑफ द विंड विल बी मच हायर. ठीक है, आज के लिए काफी है इतना. थैंक यू एंड टेक केयर. टुमारो विल डिस्कस एयर मास, फ्रंट्स एंड साइक्लोन. साइक्लोन कल ही कर देंगे.